Hello everyone. So today we are going to discuss about isolated footing. So I think you all know about what is footing. So footing is a structural element which transfers the load of the structure to the soil. Okay. So we are going to there are different types of footings such as isolated footing, then combined footings, then we have strip footing, or strap footing. So these are basically shallow footing, shallow foundation. We have deep foundation also like pile and well. I think you already know about this. So today we are going to discuss about isolated footing. Okay. So let's take an example. Design an isolated footing for a column of 300 by 500 mm. The column dimension is given to you. Reinforced with 625 mm bars with Fe415 steel and M25 concrete. This is for column. These two are for columns, okay? And which is subjected to an factored axial load. Try to concentrate over this term, factored axial load. That means what? This 1000 kilonewton that you are looking at, this is Pu. If I say 1000 kilonewton, then it has been already been multiplied with a factor of partial safety factor of 1.5. It is already multiplied in it. Okay. So this is factored load and a factored uniaxial moment MUX 120 kilonewton with respect to the measure axis. So whenever in the question it is mentioned like measure axis, suppose we have a column, the column dimension is already given to us, which is 300 by 500. Suppose this is the center, then in that case the axis about which the section is stronger will be called major axis. Major axis will be the axis which is stronger against what? Deflection. Then that will be called major axis, and minor axis will be about which it will be weaker. Okay, that will be called minor axis. So here if I say this is y-axis and this is x-axis, in that case it is acting about an axis about which it is stronger as a major, or that is a major axis. So the moment is acting about this one because about x-axis it is stronger, right? About x-axis, if I want to deflect it, it will be more stronger than y-axis. So the moment is acting about the major axis, that means the axis about which the section is stronger. So it will be mx. Okay, it is acting about x-axis. X is the major axis, y is the minor axis over here. X is the major axis and y is the minor axis. And if you ask me how to find out whether it's a stronger axis or a weaker axis for deflection, then you can just find out the moment of inertia. Moment of inertia is what? BD cube by 12. If this is the section, if suppose the section is deflecting about this axis, if this is B, then it will be D, and the moment of inertia will be this much about whatever axis it is. I is more, if I is more, then that particular axis will be stronger. Okay, just find out the moment of inertia, or you can, what you can do, the axis which cuts the section or the longer section, the axis which cuts the longer section will be the major axis. That also you can say. Okay, that also you can say. The axis which cuts the longer section will be the major axis, and the axis which cuts the weaker section or the shorter section that will be the minor axis. Okay, so I think this idea is clear. Now let's go to the other, means the whatever is written here, that assume that the moment is reversible. That means either suppose this is y-axis, I'm saying this is x-axis, moment is acting like this, mx, it may be acting this way or this way, it is reversible. Okay, it might be about this side, positive and negative, both sides it can act. The shape bearing capacity may be taken as 200 kilonewton per meter square at the depth of 1.2 meter. That means this is the depth of foundation. I think in the soil you have studied, geotechnical engineering you have studied that this is the depth of foundation. This is 1.2 meter, and at this space the safe bearing capacity is 200 kilonewton per meter square. And what is safe bearing capacity? Safe bearing capacity is the Q net divided by factor of safety plus the surcharge load, or you can say I can say gamma into df. This is the equation for safe bearing capacity. So simply what I can say, safe bearing capacity is the capacity of the soil which it can take, or the load it can take without failing in settlement as well as shear. Okay, and in safe bearing capacity, as you can see, the factor of safety is already being taken care of. This point is very important while we will be doing our design, that the factor of safety is already taken care of in safe bearing capacity. Now the thing is, while we design a building, while calculating the load, we calculate the design load, right? Design load. And what is design load? If suppose design load, LD suppose is that, let me write it something else. Suppose LDL, this is a dead load, I say dead load D. That means this is a design load. Design load will be how much? Is equal to 1.5 of the working load, right? Whatever actually the load is coming, that multiplied with 1.5 to get the design load. And we design the beams, columns, the members, everything we design with what? The design load, right? That means already multiplied with 1.5. Now, or you can say this is a factored load. So here it is 1000 kilonewton as well as 120 kilonewton per meter, sorry, kilonewton meter, both are actually design load, right? They both are actually design load. So that means what? The already partial safety factor is there. Now again, if you see the shape bearing capacity, here also factor of safety is taken care of. If I design for this load considering this directly 2000 kilonewton per meter square of factor of safety, what will happen? Suppose already 1.5 factor of safety is there for the from the load point of view, as well as factor of safety from the stability point, means from the structure capacity of the soil point of view. So total, if suppose normally in case of soil it is taken as suppose 2.5 or 3 sometimes. Okay, so suppose it takes a 3, so then total factor of safety, that means if I consider directly this 1000 and calculate for this 2000 kilonewton per meter square of soil capacity, then total factor of safety becomes how much? 1.5 times of 2.5 or 1.5 times of 3. So it becomes very large capacity you consider. So that means what? You are considering some excess amount of factor of safety for the structure or for the footing. So what we do while means finding out the geometry of the structure of the footing. Okay, so this is only valid for footing. So when we will be finding out the shape and sizes of the footing, when we find out the size of the footing, so what we do to minimize the factor of safety, we consider the working load, not the design load. Design load is not taken, working load is taken. Working load, or that means what? if I have a design load of 1000 kilonewton, then the working load will be 1000 divided by 1.5. This is taken for calculation of the soil pressure and the soil stresses. Understood? So to minimize the factor of safety, as we already have factor of safety considered for the safe bearing capacity. Okay, so this is how it is done. You will understand why we will solve the problem. So now let's look at the datas which will be required. So total load on the column, which is PUC, this is the design load, which is given by 1000 kilonewton. Now if you see, the footing is basically placed at a certain depth from the soil, right? Suppose this is the soil level. Now if I'm talking about the soil at this level, this person, so here we have the soil. So what is the load that is coming to this soil? So we already have the P, that is the axial load, as well as we will be having soil over here also, and also the weight, the self weight of the footing also will be there, right? So as you can see that at this level the soil will be subjected to the axial load as well as the self weight plus any surcharge load that is over the footing, any surcharge load that is over the footing. Okay, so to take care of that, let us assume that this surcharge load, either including self weight plus the any soil which is over the footing, adding all this, let us assume that it is taken about 15% of the total load. It is just an assumption. Okay, and the final load of the soil, as 15% we can increase whatever we have considered. Okay, so the total design or factored load on the soil at the depth of, or um, at the edge of the footing will be PUC into 1.15. Okay, that will give you 1150 kilonewton. Then total moment major axis, MX is 120 kilonewton meter. So this is also design moment. Then size of the column which is already given to you. So I'm assuming what? So let me show you the figure. Yeah, look at this figure. So suppose this is our footing, this is our column. This is 300 this side and 500 this side. So in that case, we as and this is suppose the y-axis and this is the x-axis. Okay, so now this side which is along the y-axis I am denoting as cy, and which is along the x-axis I am denoting as cx, column sizes cx and cy. Okay, so anything you can assume, this is what I have adopted. So Cx is 300 and Cy is 500. Okay. Then the materials are different for both column and footing. So for the column FCK is M25, Fy is 415, and for footing it is M20 and Fe 415. Okay. And shape bearing capacity, which is 200 kN per meter square, which is at the depth of the footing is given as 1.25 meters. Okay, now let's go to the dimensioning. Now first step of the footing design is the dimensioning. That means what should be the size of the footing so that it can transfer the load to the soil without creating um, pressure which is more than the safe bearing capacity. Okay, so first of all just look at this figure. So before, while you will be solving this problem in means in the exam, so always draw these figures. Without these figures, you will be confused. So first draw this figure. You can see this is a column. This is actually the view we are looking at from this side. If this is the plan view, then we are looking from this side. Okay, so this is 500. Okay, now the moment is acting something like this. I told you it is major axis. So x is the major axis, y is the minor axis over here. and the moment is acting about the major axis. So it will be acting this like this. So it is mentioned, it is shown over here, this is the moment. Now if you see, for I think I don't know whether you have learned it or not. So whenever we have a footing, if I give a point load to it, okay, suppose we have a footing without any moment and only point load P. I think in the column part I have discussed this portion. That then what will happen, the stress from the soil will be uniform, it's just a rectangular type, right? So which is, if A is the cross sectional area, then it will be P by A, right? And if I have a moment along with, suppose we have a moment to the footing, in that case what will happen, the stress will be varying. Suppose only moment, I am considering only for the moment distribution diagram, okay? So in that case what will happen, along, if as moment is acting in this side, so compression will occur, so the reactions of from the soil will be upward, and this side tension will occur, so reaction will be downward. Okay, and what are these values? This is m by z. What is z? Z is the section modulus, that is b t square by 6. Okay, now if I combine these two, this is for axial load and this is for moment. Okay, and if I combine these two, we can get either something like this or something like this probably, or something like this, depending upon this variations will depend upon the values of p by a and m by z, because the values are nothing but in this side it will be, see along this side, if I show you over here, along this side these are tension zone, right? So here we have that is a downward direction, so here this will be, we can say, negative, and this will be positive side, right? So at this part means, if this is the center line, then at the above means on the right side and the left side we'll be having p by a minus m by z, and on the right side it will be p by a plus m by z. Okay, so we, if the mz value is larger, then we will be having a negative portion over here, and if so, and this is the blue portion is suppose the positive portion, the upward direction, and if suppose p by a and m by z are equal, then it will be 0, then the whole diagram, whole stress distribution diagram will be under compression, or the soil will be under compression, right? Something like this kind of stress distribution diagram you will observe. Now the thing is, while designing a footing you should take care of whether along all the section of the footing no tension has developed. Okay, you have to take care of that, that no tension develop along the footing. That means what, here you can see a red portion, that means this kind of condition is not advisable in case of footing design. Why? So if there is a tension over here, suppose I'm talking about this part where I'm having a tension over here, in that case this part of the footing becomes useless for us, because this portion cannot transfer the load of the structure to the ground, because it will move upward, and means as the moment will act, then ultimately the footing it will tilt, and it will be having a shape or deflection, or say rotation, something like this, right? So as the tension develops, so this portion becomes useless for us. We have only a limited portion, this portion is available with us. Okay, so that is why we, or it is not suggested to have tension. So always try to have a compression. That means this is the minimum criteria to design a footing. So the stress distribution should be something like this, where one side we can have minimum 0 and other side we can have maximum. That means tension is should not be there, tension should be 0. Okay, so if this condition to be satisfied, if I want to satisfy this condition, there is a solution to find out, means at what location or what should be the eccentricity of the moment. So let's try to find out that. So as you can see, this should be 0 as tension is not allowed. So just look at this. Here I can write P by A minus M by Z should be equal to 0. Okay, or what I can write, this should be greater than 0, right? Now we know that M is nothing but P into eccentricity, right? This is already known to us. And area is nothing but, suppose I write it small b and small d. Okay, width and depth, don't consider anything effective depth, nothing like that I am considered here. Just assume to be b is the small b is the width, d is the depth, this dimension. Okay, suppose this is b, this is d, something like that. Okay, so area will be, area of the section will be b into d. And what will be the z? Z will be, for this case, b d square by 6, right? D is the depth, b is the width. So these are normal equations that you already know. So let's rewrite this equation. P A is bd minus m means p into e, and z is nothing but b d square by 6, which should be greater than 0, right? Okay, now look at here. So if I take p by bd common, if I take this out, then what I can write, 1 minus e into 6 into d greater than 0. This I can write, right? P by bd, I take it out. Then that means what? The multiplication of p by bd whole into 1 minus 6 e by d is greater than 0. That means what? Both of them should be greater than 0. That means either you can write p by bd should be greater than 0, and this is not or, this should be and, both 6e by d should be greater than 0. Now we will concentrate over this. Okay, we will just concentrate over this. Just let me remove other part. Now just concentrate over this. 1 minus 6e by d should be greater than 0, right? So what I can write, if I put the 6e by d on this side, then I have to add both sides 6e by d, so it will be 1 should be greater than 6e by d, right? Or what you can write, d by 6 greater than e. Um, yeah, that means e should be greater than d by 6. Yeah, so sorry, so here I should write, so you should say that e should be less than d by 6. So what is d basically? If I have already mentioned that b and d's are width and length, right? So b is, suppose I say capital B, d suppose I say capital L. In that case b is less than L by 6. So if this condition is satisfied, then I can say this p by a minus m by z will be always greater than 0. So to have this condition satisfied, I should always take care of this condition. That means the e should be less than L by 6. Understood? So what is e? E is nothing but m by p. Okay, if e is less than L by 6, in that case your footing will not be having any tension over its whole length. Okay, so that means we have to check for this case. Okay, understood this part? I hope you have understood. If you have any doubt, please let me know. Now let's see our calculation to find out the dimension. So first of all, as I have already told you, for dimensioning we will be not using the design loads, we will be using the working stress, sorry, the working load. Okay, so I first convert it to working load. So that means design load divided by 1.5. This is 766, and for the moment also it becomes 80. Now what will be the eccentricity over here? Mx by p. This is mx and this is p. Okay, mx by p, which comes out to be 104.348. This is the eccentricity over here. Now our condition that just now we have derived is E should be less than L by 6 or L should be greater than 6E, right? That means the length of the footing, if this is the width, this suppose this is the B and C L, then the length of the footing should be more than 6 times of the eccentricity, which comes out to be around 626.086 mm. Okay, so this should be the minimum length of L. So this is one condition that we have got. This condition should be satisfied. Okay, now this is what I have written. So L required is greater than 626 mm. It should be, means while dimensioning you have to take care of this, that your length should be more than 626 mm. Now again, previously we have seen that the maximum stress will be nothing but P by A plus M by Z, right? And this maximum stress, what should be? This value should be always less than safe bearing capacity, because this is the safe bearing capacity. So whatever stress that is being developed because of the point load as well as the moment should be less than the safe bearing capacity, otherwise the soil will fail. So our condition is P by BL, that is P by A, plus M by Z, that is M by BL square by 6, should be less than SBC. Okay, so in this question we have the moment about the major axis, so it becomes L over here. If it's in the shorter side, then you have to take care of that also. Okay, in that case probably it will be B. You will understand this once you go in deep and try to figure out the steps. Okay, now so if this condition to satisfy this condition, so let us assume that the width of the footing is 2 meter, just an assumption. Okay, and if we put the value of B, P and Mx everything, and it should be less than as BC, and if we solve it for L, then we can get L as two values over here. One is minus 0.497 meter and one is 2.41 meter. Okay, so as this is not possible, so the length is 2.41 meter. It should be more than 2.41 meter. So let us assume that length is 2.45 meter and the width is 2 meter. Okay, so this is our assumption. And also it has some of the book, you will see that the dimension of the footing should be should the ratio of the dimension of the footing should be in line with the ratio of the dimension of the column. That means we have a column of 500 by 300, so the ratio will be 5 by 3, sorry, 5 by 3. And here also the ratio should be equal to, means the ratio of the footing and the ratio of the column should be same. Okay, in sub book you will get this. Okay, so if you do like this also, there is no issue, but the thing is our criteria, this criteria should be fulfilled. Okay, that means the total maximum stress should be less than stress bearing capacity, as well as from the criteria of E should be less than L by 6. This criteria should also be followed. From this we get around L should be more than 600 mm, around 646 mm. So we have assumed 245. So obviously this condition is satisfied. That means in the footing nowhere will be having tension. All the footing will be under compression. Okay. So this is what we have assumed for now. So while you'll be solving problems, you might assume something else also. Okay, so this is one criteria how you can choose the B also, B here. B or L. Okay, so this depends how you choose. It may be 2. This assumption of the dimension also depends on some site factors also. Site factors means what? Suppose you have your building just at the edge. Suppose this footing is just at the edge of the boundary of the plot where you are constructing. In that case, your footing might not you might not have the liberty to extend the footing, as there is a boundary issue. In that case, you might have to limit the width or length. That's how exactly you have to find out. This is from your engineering judgment. Okay, this is how by using engineering judgment you have to select the width. Now let's go for, okay, now cantilever, yeah, this is the width and this is the depth, so this is the figure. So, and what will be the cantilever projection on the longer side? That means cantilever projection means from the face of the column to the edge of the footing, which is total length is L, then L is 2.45 meter. Cy, I told you this side I'm assuming it to be Cy, so this is minus Cy by 2, then we will get this length. Okay, so this is the cantilever projection, which is I have denoted by C. So C is nothing but 975. So we will be requiring this value, so I have calculated it over here. So you can find this problem in Pillai Menon book. You can refer to that book also. Now next step is to find out the pressure and that maximum the pressure values or the stress values of the soil. So the maximum stress will be for whatever dimensions we have considered will be 264 and 114 maximum and minimum. Now take care or give very or concentrate over this factor that here we have not used the working load. We have not used this. We have used the design load over here, because the stresses that we have calculated, this will be used for designing. This will be used for designing of footing. So as far as the limit state theory is concerned, we have to take design load, right? So working stress load is only taken for what? For dimensioning, to find out L and B. To find out what is L, what is B, we have to take care of we have to consider the working load. Okay, other than that, for designing purpose you have to use the design load. So finding out the maximum stresses, you can see PUC I have taken, that is maximum, which was 1000 and which was it is on 120, so that we have taken. And also from the stress value you will see that it is 264, which is more greater than 200, which was the safe bearing capacity. Okay, so don't confuse. So while we'll be designing, we have to consider the design shear stresses or the design stress distribution. So here we'll be using the design loads. Okay, because this will be used for designing. Also, I should mention here that the load combinations that you use for um, building design, we use 1.5 dead load plus live load, then 1.2 dead load plus live load plus earthquake load, or 1.5 dead load plus earthquake load. So as per IS 1893, you can check in this code that whenever there is a earthquake load, then we can increase the safe bearing capacity depending upon the soil condition. If the soil condition is very good, very hard soil, we can increase the safe bearing capacity. Probably I forgot the value, but I think around 50% we can increase. If it's a medium soil, we can go for 30%, and if it's a loose soil, it is a 0%. That means for a bad soil, which is a very loose soil, you cannot do this. But if it's a medium soil, you can go for 30% increase, and if it's a very hard soil, you can go for 50% increase in the shape bearing capacity. Okay, so this is basically depending or considering the um, probability of occurrence of earthquake load, because earthquake load is going to come say once in 50 years, one in 60 years, right? So in that case, no need to consider that excess amount of loading, because for earthquake load the moment will be very high, the loads will be very high, the size of the footing will be very high. So that is why, while there is a combination, suppose this critical combination you got over here is considering the earthquake load, in that case you can increase the shape bearing capacity by certain percentages. I'm not very sure about the values. You should refer to 1893. Depending upon the soil condition, you can increase the shape bearing capacity so that we can reduce the size of the footing by certain amount. Okay, then let's go for thickness of the footing. So I think this part I will cover in the next class. So for today's class, what we have discussed how to dimension, and how to find out the stresses, soil stresses, and how to find out the dimension of the footing. In the next class, we will go for how to find out the depth of the footing. That means one-way shear and two-way shear, that we will discuss. Okay. So if you have any doubt, please let me know. Thank you.